In this video, I'm going to show you one way to store a stack in an array in C. I'll do this again after we have structs, because we can use them to clean up the parameters to these functions. This slide is from my video about storing stacks in arrays in general. Check out the link above if you need an explanation. In this video, I'm going to show you how we do these things in C. So, there are a few language-specific issues that we're going to need to address. First, this implementation does not need malloc or structs. I'll be able to do a cleaner implementation when we have those, and I'll add a link above when I get that video posted. In this example, I'm making the stack hold characters, but we could change that to hold any type. We need three things: the array, an int holding the index of the top of the stack, and the size of the array. For demonstration purposes, we'll store the stack in an array that is a local variable that is not dynamically allocated. But it could be dynamically allocated without changing any of our stack functions. I've used a pound define for the size of the array, but you could make it a variable if you wanted. The big challenge with the C implementation is how do we let the callers of push and pop know if their requests were unable to be fulfilled? For example, what do we do if someone tries to pop a character from a stack that's empty? My strategy for handling those things consistently is that push and pop will return a Boolean, true if they worked and false if they didn't. That means, compared to the general solution I gave in the previous video, pop will now need an extra output parameter to give back the value that it popped. We need a consistent strategy for the position stack top should be referencing. While there are other rules that would work, I'm making the rule that stack top will index the array right below where the next entry will be added. So, if there's data in the stack, stack top will index the topmost data in the stack. If there is no data in the stack, then stack top will be -1 because the next thing will be added at position 0. Having picked that rule, we now can calculate the conditions of stack empty and stack full. The stack is empty when stack top is -1, and it is full when stack top indexes the last position in the array. The value of that is the size of the stack -1. Now we're ready to start. Creating a new stack just requires that we allocate the space for the stack, remember how big the stack is, and set stack top to -1. Push is a little more complicated. It has 4 parameters. The first is the data we want to push onto the stack. The second is the array that is holding the stack, and it's an input-output parameter. It has data, and we need to be able to change that data. Remember, while it looks like we're passing the whole array into the function, the compiler only passes a pointer to the array. So when we change stuff in the stack, we're changing in the one copy of the stack that exists, the original array that we allocated. The third parameter is stack top pointer, and again, it's an input-output parameter. It tells us where the top of stack is when it comes in, and if our push is successful, we'll have to increment it to have that value passed back. Therefore, in this function, stack top pointer is an integer pointer pointing at an integer variable in the prior stack frame. That means that, in order to get the value that stack top pointer points at, we're going to have to dereference it every time we use it. The fourth parameter is the size of our stack. It's just an integer because we don't need to be able to change it. My strategy for push is this. First, we can only push if the stack isn't full. In that case, increment the int that stack top pointer points at, and then use that int to index the array and store the new item in that position. We were successful, so we return true. If there wasn't room in the stack, just return false. We can't push anymore. Here's the code to do that. This is checking to see if there's room left in the stack. Here, we are dereferencing stack top pointer to get the int that it's pointing at, and then incrementing that int. Then, we dereference stack top pointer again to get the new stack top value, and use it to index the stack's array to store the item there. To play with this, let's push something onto an empty stack. Here's the code that creates a stack and puts -1 into stack top. This call on push should put a capital A onto the stack. Our parameters are the item we want to push, the array holding the stack, the address of stack top, since we need to pass a pointer, and the size of the stack. The first thing push does is compare the -1 that stack top pointer points at with the size of the stack. Since there's room left, we go into the if. Then we chase stack top pointer and increment what it points at, so that will make stack top become 0. Then we chase stack top pointer again to get that 0 and store our capital A in the position of 0 of the stack. Return true because it works. The important thing to remember is that stack top pointer is pointing to the integer we want to use. So every time we use it, we have to dereference it to get that integer. Once you've figured out push, pop isn't so bad. 3 parameters: our stack, the pointer to our stack top, and a pointer to where we should store the thing we popped. The code checks to make sure our stack isn't empty. If so, it stores the thing that is in the position stack top pointer's int indexes, and then decrements the integer that stack top pointer points at and returns true. If the stack was empty, it just returns false. So why would we do this? Let's build code that will take input from a user 1 character at a time until they enter a %sign, and then output what they gave us in reverse order. To do that, I first made a function to get 1 character from the user. Note that the carriage return that the user types at the end of each line is also a character, so we have to read that just to ignore it. With that, my code to reverse the input is just 2 loops. The first gets input from the user and pushes it onto the stack. It keeps going until either the user enters a %sign or the stack is full. We detect full by we try to push something and it returns false. So worked becomes false. Once that loop finishes, then we need a loop to pop things off the stack and print them out until the stack is empty. So that's it. That's how we can store a stack in an array in C. Watch for another version that uses a struct to put together all of the stuff that we need for a stack, so we don't have to keep passing the array and the stack top and the stack size separately.